Hi everyone. In our last video, we mainly talk about mole concept, which was one of the important properties of gases. And we have the other properties like pressure, temperature, and volume. Now, in this video, we're going to look the relation between all these properties of gases. Okay, let's start with the first one. The name of the first law is Bernoulli-Moriarty's law. Now, in this law, the relation between the pressure and the volume is identified. But in order to just see the relation between the pressure and the volume, all the data should be constant, like the temperature and amount of substance, which is in fact the mole number. And also, according to identify this relation again, you should use a container with a piston here. This is a piston, which is also called an ideal piston. Why should I use this container? Because the volume should be changeable. If you use a closed container, a constant volume container, in this case, you cannot see the relation between the pressure and the volume. So as you see, the container is divided into units. And let me give number to those units. Let's say that this part is 1 liter, 1 liter, 1 liter, and 1 liter. So this has a 4 liter container. What about this one? 1, again 1, again 1. So this is a 3 liter container. This is 1 also. This is 1 also. This is also 2 liter container. So let's say that you have an elastic balloon, and when you squeeze that balloon with your hands, what happens to the balloon? Finally, probably it explodes, because it is going to have a really high pressure when you decrease the volume of that balloon. So the same thing is valid for the gases also. So this means that the pressure and the volume are related to each other indirectly. When you decrease the volume, the pressure is going to be increased. So let's say that the pressure of the first container is 3 atm. So what would be the pressure of the second container? So as you see here, the volume is decreased by 3/4. So this means that the pressure is increased by 4/3. So the new pressure becomes 4 atm. So what about last one? As you can see, in this case, the volume is just directly halved here. So this means that you're going to double the pressure. It was 3 atm, now this is going to be 6 atm. So look at what happens when you multiply the pressure by the volume for each container. First one, volume times pressure makes 12 here. Volume times pressure makes 12 again, and volume times pressure makes 12 again. So this means that pressure times volume should always be equal to a constant. So when you increase the volume, the pressure should be decreased, or vice versa. So what kind of a graphic would you have? It is going to be an indirect ratio graphic, and it's going to be like this. So if you like to formalize this relation, you can formalize it as pressure 1 times volume 1 should be equal to pressure 2 times volume 2. The second law is named as Charles' law. In this case, it indicates the relation between the temperature and the volume. So what do you think, what kind of relation does it have? When you increase the temperature of a gas, what happens to the volume of the gas? Of course, it expands. I can hear your answer. So mole number and pressure should be constant when you measure that relation. So what kind of container you should use? You should use a container with an ideal piston. Ideal piston means it keeps the pressure of the container always equal to the pressure outside. If it's kept, of course, at the same place, at the sea level always, or at the peak of a mountain always, but it should be at the same place. Ideal piston means it has no friction, and its mass is not encountered, meaning not important. So instead of ideal piston, in some of the question, you're going to see that elastic balloon is used. So again, balloon keeps the pressure inside equal to outside. So again, just let me divide the units to liters in the first piston. 1 liter, 1 liter, so this is 2 liter. This is 1 liter, 1 liter, 1 liter, 1 liter, so this is 4 liter. So as you see, the volume is doubled. So what about the temperature? Is this doubled? Here is my question mark. When you use the temperature in these questions, you should have used them in unit of Kelvin. So just I erase this 0 Celsius and I make it as 273 Kelvin, and I erase this one also, I use it as 546 Kelvin. Now, is it doubled at the moment? Yes, in the unit of Kelvin, this is doubled. So this means that volume over temperature is always equal to a constant. So when you increase the temperature, the volume is increased also. It equals to a constant number. So if you just formalize it, it's going to be like volume 1 over volume 2 equals to temperature 1 over temperature 2. So why do I have two graphics here? Because there are two important units of temperature. First one is the unit of Kelvin, and the second one is the unit of Celsius, and this y-axis are volume. So when you draw the graphic for Kelvin, the exploration starts from 0 and goes like this, and for Celsius, the exploration starts from minus 273 and goes like this. And this point, this 0 Kelvin and minus 273 Celsius is known as absolute zero temperature. The name of the third law is Gay-Lussac law. It indicates the relation between the temperature and the pressure. In this case, you have a container with a constant volume and with specific amount of gas in it. When you increase the temperature, this means that the kinetic energy increases, so does the pressure of the gas inside the container. So this means that temperature over pressure always equals to a constant. They have a direct ratio. And if you just like to formalize it, you can formalize it as temperature 1 over temperature 2 equals to pressure 1 over pressure 2. So when you draw its graphics, again you have two kinds of units of temperature. One is Kelvin and the other one is Celsius. The first one is accelerated to 0 like this, and the second one is accelerated to 200 and minus 273 like this, again indicating the direct ratio between these two variable data. The fourth one is Avogadro's law, which depended on the mole and volume relation. In this case, again, you have a container with a piston here, and the idea is, in this case, at the same conditions, equal mole number of gas particles occupy same amount of volume. So let's say that you have again 1 liter, 1 liter, and 1 liter here. In total, you have 3 liters. You have 1 liter, 1 liter. In total, there's 2 liters. So let me give you that the first mole number is, let's say 6 mole. So what should be this one? So if they have a direct ratio, if this is 6 mole and this should be 4 mole. So what kind of graphic would they have? This is mole, this is volume. So if there is no gas, there's not going to be volume occupied. So it goes like this, starting from 0, and it directly increases like this. The last one I'd like to talk about is Dalton's law of partial pressure. In this case, you again have a constant volume container. This is volume is constant, where the temperature should be constant also. And you have different types of gases. For example, you have 2 moles of nitrogen gas inside it, and 4 moles of helium gas. So let's say that this container has a total pressure of 12 atm. You can find the pressure of nitrogen and pressure of helium separately. Now, which I mean, if you have total pressure of, when you sum this 2 by 4 here, you're going to find 6 moles. If total mole number of is 6 mole and total pressure is 12 atm, so you have nitrogen as 2 mole here, so its pressure is going to be 4 atm. And if you have some helium here with a mole number of 4 mole, then its pressure is going to be, in this case, 8 atm. So what I mean is here, the number of moles is directly proportional to their pressures. 6 mole refers to 12 atm, 2 mole refers to 4 atm, where 4 mole refers to 8 atm. So this is known as Dalton's law of partial pressure when they are in the same container and when they are at the same temperature.